Hey guys, Buildzoid here, and today we're going to be taking a look at the voltage regulation of yet another Z790 motherboard, this time the MSI Z790 Godlike, which was very generously donated by a fan of the channel. And so, yeah, big thank you to them for sending this board over, because it is very expensive. Now then, for the test setup, the CPU is a 13900K. It is underclocked because during, measuring, I don't want the CPU crashing. So we're at 5.2 on the P cores, 4.2 on the E cores, and 4.4 on the ring. So yeah, I mean, we're also going to go over the voltages, but not right now. Well, the voltage settings, but not right now. For the actual probing setup, the oscilloscope is connected to the back of the CPU socket with some coax. That connection looks like this. There's a 50 ohm termination at the oscilloscope, and the issue with this probing methodology is that, yes, it's very convenient because you can just solder coax to the, to like the Vcore capacitors of the motherboard, and then you get your measurement. But the downside with this is that LGA CPU sockets have a lot of impedance. So basically they have a lot of inductance and a lot of resistance to them. And that means that we don't actually see, like, ideally we would want to be measuring what is happening to the core voltage at the actual silicon. But we're not doing that because we're behind the impedance of the CPU socket. So in theory, we should be seeing less undershoot because the undershoot sort of starts at the CPU because it's caused by the CPU suddenly going, like, you can sort of think of it as the CPU going low resistance out of nowhere. And so then the VRM needs to ramp up the output current, and it can't react instantly, so you initially get a, voltage undershoot due to the delay between the CPU basically going low resistance and the VRM actually being able to react to that. So that, so the undershoot basically starts at the silicon, and so if we're measuring it at the back of the motherboard socket, we're actually going to be potentially seeing less of that because the inductance of the socket, as well as the CPU substrate and the resistance of the socket and the CPU substrate will actually attenuate that before, it gets to where the coax is connected. And then we should be seeing more overshoot because overshoot is happens when the CPU goes from low resistance to high resistance, and this is a gross simplification of what the CPU is actually doing, but that's the convenient way to think about it, because the CPU doesn't, the VRM doesn't push current, and the CPU doesn't pull current, because that leads to some weird assumptions about how things work. So you can think of the CPU going low resistance to high resistance, and then from high resistance to low resistance. But anyway, so when the CPU transitions from low resistance to high resistance, the excess energy stored up in the inductors basically translates into a big voltage spike. And the inductors are basically directly connected to where we're measuring at, right? So, well, they're not directly connected to where we're measuring it at, but we're going to see more overshoot because that's local from the motherboard, and that overshoot will potentially get somewhat attenuated by the CPU socket, though it should be less of an issue than the attenuation of the undershoot to the back of the socket. This method works really well on GPUs, though. By comparison, on motherboards, the LGA socket and the substrate of CPUs is actually a really, they're not great in terms of, power delivery. For comparison, measuring GPUs like this actually works really, really well. Yeah, there's very little impedance between the back of a GPU core, the back of a GPU PCB, and the actual silicon itself, because you don't have pins connecting it. So anyway, that's the test setup. Now let's get some measurements. The goal here is very simple. We want to see as little undershoot as possible, so we want this minimum voltage measurement to be as close to the average voltage measurement when the CPU is actually under load and going through transients, because yeah, CPUs don't actually, maintain a fixed amount of current drop under most circumstances. I mean, right now it's pulling a relatively fixed amount of current because we're literally just sitting idle in the BIOS, but yeah, anyway. I also have the max voltage here, which will show us the overshoot, and then we have peak to peak. Peak to peak is a funny measurement because it doesn't really mean anything, but, it's nice when it's low. But yeah, from a, like an overclocking perspective, it actually has very little significance. So anyway, for the settings, we're going to be starting with a 0 V-droop setup. So 1.24 volts on the core voltage, and mode 1 LLC, which yeah, has no V-droop on this motherboard. I know that the graph over here on the side shows that we'll actually get like extra voltage, but that only happens on the back of the CPU socket. That doesn't actually happen at the CPU. And this motherboard does actually have like hardware info has support for the VRM controller that's on this board, so you can actually get a VR/Vout voltage reading, which is directly from the VRM controller, and that's like your most accurate like average core voltage reading, because the VRM technically, well, it won't measure the undershoot and it won't measure the overshoot, but it'll give you a very accurate average core voltage reading. So that's what we'll look at that when we're in the OS and actually running the workload. Anyway, for the other settings, load line saturation for now is disabled. Over voltage protection, I have that maxed out. Over current protection, I have that maxed out. CPU switching free, VRMs. Yeah, this really should be called Vcore VRM switching frequency rather than CPU switching frequency. But anyway, yeah, so the switching frequency of the Vcore VRM is currently set to 500 kilohertz. I have tested if setting it to 1000 kilohertz does anything. And the answer is, if it makes a difference, it's beyond the capabilities of, it's beyond my measurement capabilities. So basically, I don't think it actually does anything, which is not surprising. Most high-end motherboards don't generally see a difference in terms of voltage regulation from adjusting the VRM switching frequency. Because most high-end voltage regulators will actually have a, will potentially skip PWM pulses or add PWM pulses for large transients. So the switching frequency really isn't the switching frequency is more of a steady state setting rather than something that really affects transient response from the VRM. So anyway, let's not make any changes and get into Windows to... Oh, I guess I still want to have this kind of blown up so that you can see the VR/Vout sensor. Actually, I'm going to have to make this bigger for that. Oh, also, I forgot to mention that right now we're testing on the VCC Sense setting, which we'll get to. We'll also take a look at Socket Sense. Because Socket Sense is actually... Socket Sense gives you, somewhat better options for the load line calibration settings. Because on VCC Sense, your first 5 LLC settings... Okay, not 5, but, your first 4 LLC settings are kind of the same thing. So, anyway, here we are in Windows, and we'll start hardware info. And then we'll start Y-Cruncher. And so now if we scroll down over here, so this is the VR/Vout sensor, and you can see that that's sitting at 1.24 volts. And then you have the core voltage sensor on the motherboard itself, and you can see that that's actually reading a bit higher. Not much higher. Oh, right, because this has that wacky VCC Sense thing. Yeah, so this board, so this is a... So MSI, I'm not 100% certain on what exactly, the MSI VCC Sense is. My theory as to what it is that they're taking the, part of the DyeSense voltage reading and referencing it against, local ground at the Super I/O, which is, not really what, that's not great. But anyway, so we don't really see a huge difference between VR/Vout and Vcore right now. But even then, the Vcore reading is not accurate. And also, the main point is that if I stop the workload, you can see that the Vcore reading actually drops down, right? But that's not because the board is that's not because the LLC is increasing the core voltage, because you'll see that the VR/Vout sensor, that's still at 1.24 volts, right? And this is what the actual VRM controller is regulating against, is this reading here. And this is a reading that the Super I/O on the motherboard, which is basically a chip that has like a bunch of monitoring functionality and like power. Just look up what a Super I/O is, if you want to know what that is. Like the main thing is like this sensor has nothing to do with the actual like control of the VRM. The control of the VRM is handled by this sensor over here. That's from the actual VRM controller. Anyway, so let's go back to running Y-Cruncher. And also, if you're using this board, or really any motherboard that has a VR... where did the sensor go? Did I just hide it somehow? Where'd it go? Store. Wait, I did... Oh. There. Yeah, so I did hide it. Anyway. So yeah, if you have any motherboard that has this VR V-out sensor, you should just use that sensor, because that's accurate. Anyway, now let's take a look at the oscilloscope. So first thing you'll notice is we have these spikes everywhere. And these are just from the Windows event timer, which is just how Windows makes sure that everything is running properly. Normally it runs at, I think, 16.25 milliseconds. It's like some weird... Like, if I remember correctly, it runs at like 64 hertz normally. And then if you need if Windows for some reason needs more accurate timing, it'll ramp all the way up to like 1000 hertz. So you can actually, and like in certain scenarios, these spikes will actually be occurring every millisecond. But anyway, so that's one transient, is just Windows periodically interrupting the Y-Cruncher workload to do Windows things. Then, of course, if you start moving the mouse around, well, now the OS has to start processing user input, and yeah, that makes the VRM very upset. In fact, it makes it so upset that I can hear coil whine. Which doesn't actually, like, coil whine is not, like, an indication that the VRM is, like, that's not a physical damage concern, it's just, like, annoying. And it's kind of funny that you can actually hear the effects of moving the mouse around. And, so, anyway, as you would expect from a maxed out, you know, 0 V-droop LLC setting, the voltage regulation is somewhere between not great and completely terrible. Like, it's not great when I'm not moving the mouse around, because we still have, like, very noticeable undershoot, right? Like, if I clear the... monitoring on the oscilloscope, we can see that our average voltage is at like 1.3 volts and our minimums are like 50 millivolts below that. And that's, you know, not great. Maximum voltage is somewhere around like 1.38. So I've got like 80 millivolts of overshoot here, and I'm not even really doing anything. And then if I start moving the mouse around, you know, we start seeing peak-to-peak measurements in the range of like 300 millivolts, which is quite bad. I mean, if this was a GPU, I wouldn't, especially, yeah, if this was a GPU, I wouldn't really be complaining. But for a high-end motherboard, that's actually quite bad. The overshoot hits 1.52 volts, so that's like 220 millivolts above our, you know, average voltage. So that is really not great. And our minimums hit as low as 1.18 volts. And actually, I think it might even get worse, or... Nah, yeah. So it bottoms out at like 1.188-ish volts. So that's like 120 millivolts of undershoot. So, yeah, disabling the V-droop is bad for voltage regulation. Whoever could have predicted that? So... Anyway, let's move on to some more useful LLC settings. We're going to be skipping all of the, like, we're going to skip mode 2, 3, and 4, because they all kind of suck. Like, they're really not that different from mode 1 in terms of what they do to voltage regulation, especially like mode 2 and 3, because mode 1, we're at 1.24 volts to get 1.24, like, there's no V-droop, right? So it's 1.24 volts, mode 1, which is equivalent in terms of, like, load voltage to 1.255 volts mode 2. So we're not actually gonna set the LLC that high. I mean, we're not gonna test like mode 2, 3, 4 because yeah, they still suck, and even mode 5 still has very noticeable undershoot. But mode 5 is like tolerable. on VCC Sense, almost tolerable. Anyway, for mode 5, we're going to want 1.295 volts to get the same VR Vout voltage under load. Yeah, 1.295. Also, the VCC Sense thing, that's this here. Yeah. Which I think is like, because Asus motherboards and some Gigabyte motherboards have like proper DiSense voltage sensing from the Super I/O. And I think VCC Sense is like MSI's attempt at copying that functionality, but they like did it not properly. So it like still has like you still see the voltage go up going from like idle to full load, which it's like, you know, on mode 1 LLC, which is like isn't supposed to happen. So yeah, also the VCC Sense setting over here actually changes the load line slopes. Which is why I kind of which makes me very suspicious of how this is implemented, because on Asus motherboards and Gigabyte motherboards, the DiSense voltage like the DiSense voltage monitoring functionality that they have, that doesn't affect your LLC settings because it's just implemented with a amplifier that copies the voltage reading from the DiSense circuitry over to the Super I/O. The fact that changing this setting on this board changes the load line slopes is very weird. It makes me really wonder about how they implemented this. Like, physically implemented this. Because I haven't managed to find the, like, same circuitry that you would expect. Like, on a Gigabyte board or an Asus board, if you search around the sort of VRM CPU socket area, you can usually find a little amplifier chip that handles the copying of the DiSense voltage to the Super I/O. I've not managed to find that circuitry on an MSI board. So, yeah. Kind of suspicious of how exactly that VCC Sense functionality is implemented. Because it does have some, like, strange side effects. On the flip side, the fact that you effectively get, like, extra LLC settings out of it is kind of nice. Because, yeah, like, you have more options for dialing in your load line calibration. But anyway, so we are going to check the VR Vout sensor and hardware info again, just to show that, like, I did, you know, did a good job of pre-testing all the voltages. So here we go. Y-Cruncher is running again, and we're just going to scroll down to our VR Vout sensor, which is here, and you can see we're at 1.24 volts again, right? Also, we're at 1.3 volts on the oscilloscope. Anyway, so 1.24 volts, and then the Vcore reading over here is still the same, 1.272, right? Like it's, yeah, still roughly the same. If I stop the workload, you'll see that the voltage actually comes up because now we have some V-droop. So anyway, let's start Y-Cruncher. It's kind of interesting is that you don't really see the voltage change very much on the oscilloscope because obviously the oscilloscope is hooked up to the back of the CPU socket. And so right now the V-droop is sort of like matched to the, like, yeah, you can sort of think of it as it's kind of matched to the resistance of the CPU socket, but it's not perfect because, yeah, we still get, like, we still get undershoot, which is not ideal. So I'm going to clear. Now, right now, if we just let the system sit, the peak-to-peak reading is actually not too bad. We still have roughly, you know, 70-ish millivolts of, 70 millivolts of overshoot, but that really isn't concerning from, like, a overclocking perspective. Like, the overshoot isn't really concerning until it's so high that it might start actually damaging the silicon, which for, I think for 13th gen CPUs, that should be somewhere in the range of, like, 1.6 volts of overshoot, which, yeah, even with mode 1 LLC, we weren't, you know, like, we were getting close, but not there yet, right? We were at, like, 1.52. Anyway, average voltage is still around 1.3, and Vmin right now, I mean, if I clear it, is actually really close to our average voltage, right? We're like 25 millivolts below, which it doesn't really like you're not going to have the minimum voltage equal to the average voltage. That's just not going to happen. You know, there's always going to be some amount of like switching noise from the CPU on the waveform, as well as like the main transients that you get, which are technically just like a different type of switching noise from the CPU. There's also some switching noise from the VRM itself, but compared to the like effects of the CPU actually running, the ripple from the VRM is basically irrelevant. Anyway, yeah, so if I don't touch the mouse, this looks pretty good. If I do touch the mouse, the overshoot, I mean, the overshoot doesn't really change. So that's good, right? On mode 1, if I started moving the mouse around, the overshoot went through the roof. It does get a little bit worse, but it doesn't, you know, it doesn't turn into the 1.52-ish thing that we saw previously. And our undershoot is now, instead of like 100, what was it, 120-ish millivolts, we're now at around 80 millivolts of undershoot. So, you know, not great, but at least we're not seeing like honestly, the fact that the overshoot previously was hitting like 1.52 volts, that kind of looks like there's some kind of flaw in the set, like VRM control loop, where it's like overcompensating, and that's creating the massive overshoot. Because that really, you shouldn't really be seeing the overshoot change drastically between the various LLC settings. Not that much. Yeah, there shouldn't really be like 120 millivolt difference between one LLC and another LLC for the amount of overshoot that you get, in my experience. So, anyway, yeah, so that's how it runs on mode 5, and mode 5 is like not ideal, but like the reason, so I've actually done some testing on this with 13th gen now, is like if you can get the CPU to actually crash because of undershoot, and it's been really difficult, which makes me think that Intel has some kind of wacky clock stretching thing implemented. Because on AMD CPUs, if you have a significant amount of undershoot, or old Intel CPUs, if you have significant amounts of undershoot, it causes the CPU to crash very, very quickly. But yeah, I've not really managed to replicate that with 13th gen. And I'm not even sure if I could replicate that with 12th gen, because I've not checked for that on 12th gen. But with 13th gen, I've not managed to replicate that behavior. So, like, arguably, you could actually use mode 5 LLC, because the crazy overshoot that we were seeing on mode 1, that's gone. And also, that, like, crazy overshoot is actually somewhat present on the more aggressive LLC settings on this board. But yeah, mode 5, that's basically not a thing. And then the undershoot doesn't actually seem to be a real stability problem, but I might have just not done enough testing on that. So yeah, really not sure what to think of that. It could also be that like it's more important for, because in the past it used to be more important for your ring clocks than really your like core clocks. So I might just not be testing right for it, but yeah. Anyway, now here's a fun one. So going from, you know, mode 1 to mode 5 LLC, the core voltage went from, you know, what was it? We went from like 1.24, right? Mode 1, 1.24 to 1.295 at mode 5 in order to get the same VR Vout voltage under load. But once you switch from mode 5 to mode 6, instead of getting like, you know, you'd think like, oh, maybe another 15 millivolts, 20 millivolts of V-droop, nah, you get another 80 millivolts of V-droop. So we're going from 1.295 all the way to 1.375 now. And now we're actually going to have an LLC setting that even with me moving the mouse around, we're not really going to see any significant undershoot. Like, now we're getting into the territory of like, because moving the mouse around isn't the world's most scientific method of producing transients, like producing, you know, consistent transient loading on the CPU. Sorry about that. We start running into the issue of like mode 6, 7, and 8 actually measure very similar on the undershoot. To the extent that I'd say the differences are actually more down to like how lucky I get with moving the mouse around, because depending on what exactly the CPU is doing when, you know, the user input hits and how Windows decides to interact with the user input, that'll actually produce slightly different transients each time, which is why, you know, like, you need to you need to move the mouse around for a while to get like the undershoot, like the minimum undershoot to stop like coming down over time. But anyway, so yeah, we have hardware info open again. We're going to check our VR Vout voltage. Scroll, damn it. There. So VR Vout, right now we're at 1.36 volts. This is perfectly safe for long-term use. I wouldn't be concerned about that. Honestly, even up to like 1.45 idle, I wouldn't be worried about it. More than 1.45, I'd start being concerned. But 1.36, it's not anything to worry about. Anyway, let's hit Y Cruncher. And I'm a little bit low on the VR Vout voltage. Just a tad, like 2 millivolts. Unfortunately, getting the voltage to match exactly is kind of not really possible because this board only goes in 5 millivolt voltage steps. At the same time, I'd say having 1 millivolt voltage steps on a motherboard's VRM is utterly unnecessary. Because if you are tuning your overclock to the point where 1 millivolt is is what makes it stable or not, I dare say you might have problems with like the ambient air temperature affecting the stability of your system at that point, quite drastically. So, yeah, 5 millivolt voltage steps for you know, core voltage settings, I really don't think is a problem. Anyway, so we're just sitting here. Our peak to peak, you know, it's 90 millivolts, which is, you know, what like it's no apex, but at the same time, I've mentioned before that the peak to peak measurement is fun to look at and not really that useful. So, yeah, that's not really concerning. And right now the overshoot is still in that sort of, you know, okay, we're at 1.3 volts now and around that 70, 80 millivolt range for the overshoot. And if we're not doing anything, the undershoot is like 18 millivolts. So very, very little. And if I do start moving the mouse around, it drops down to like 1.27. Oh, so like 32 millivolts, 1.268 there. 1.267. So, yeah. So we get a little over 30 millivolts of undershoot, which is very good. I think the absolute lowest, like the smallest difference I've seen on like any motherboard ever between minimum and average voltage is like 15 millivolts. And I'm not even sure that that was at the same bandwidth that I'm taking this measurement right now. So yeah, 30, 33, 32 millivolts, like that is a very good result. But we can also still very clearly see that like there's downward spikes from the main body of the yellow fuzzy line. So we could actually like, once we switch to mode 7, we'll actually see even slightly less. As in, we won't even see the little like downward spikes from the fuzzy line. But in terms of the actual millivolts difference, it won't be that big. We'll go from like 32-ish to like 20-ish, maybe 25 millivolts only. So anyway, so yeah, I'd say mode 6 on VCC Sense is very much a usable LLC setting on this motherboard. Also, you could mix in the load line saturation, and actually, that's like the really probably my favorite feature of MSI motherboards, which is kind of funny because when I first heard about it, I thought like, oh, this is a stupid gimmick. This can't work, right? And that's the load line saturation function, because you can basically shave off a bunch of your idle voltage without affecting the core voltage under, like the core voltage regulation when you're under actual like high load, which is really, really cool. So anyway, and we will take a look at that, just not right now. So the next step is going to be mode 7 LLC, which is another 75 millivolts above mode 6. Also, what's kind of neat is actually when we switch to socket sense, Which one is it? And we will take a look at this. Yeah, mode 5 actually ends up being at 1.405. I mean 1.405, yeah. And that ends up being like this really nice middle ground between sort of VCC Sense mode 6 and 7. Is Socket Sense mode 5. So, yeah, but we'll take a look at that later. So yeah, now our idle voltage is getting up there. Now, because we have such a droopy LLC, our idle voltage is actually not even 1.45 volts, right? Because even at idle, the CPU pulls some current. And the way the LLC works is actually, you would get the, like when we have 1.45 volts at mode 7, we would only actually get 1.45 volts if the CPU was pulling literally 0 amps, which it doesn't because it's a CPU. And actually, well, technically, if the CPU had like very, very heavy power gating, it could probably just turn itself off completely. And then we'd see the VRM sitting at 1.45 volts, but as long as the CPU is doing basically anything, it will not be at 1.45 volts right now. Anyway, so I'm just going to pull up hardware info again. I guess I could have done this at a much lower resolution, couldn't I? Need less zoom. I go to 1366 by 768. Except now I can't find my shortcut, so that was a good idea, wasn't it? There, found the shortcut. Scroll down to our VRV out sensor, and that is currently sitting at 1.42 volts. And our Vcore sensor is at 1.43. Anyway, let's throw some load on this. I'm actually going to scroll this down a bit. Wait, why aren't you running? Oh, wait, nope, that's the wrong shortcut. Where did it go? Oh, there it is. Yeah, so our VRV out under actual load is actually, we're a bit low. So, yeah, I should have given it 5 millivolts more, because we're at 1.23 instead of 1.24. But, oh well, that's not too much of a problem. And our core voltage is at 1.265. So, yeah, evidently, I should have punched in like 1.455 or 1.46 even, instead of just 1.45 to get the voltages to match up. But, anyway, not a big deal. So, yeah, we're going to clear. And now if I move the mouse around, like, yeah, there's really pretty much nothing to see. Right, and if we look at the average voltage, that's at like 1.295-ish, and our undershoot is down to the 1.268 volt range, so that's what, like, yeah, like 25 millivolts-ish. Actually, slightly more than that. It's like 26 millivolts, right? I'm not that good at doing math in my head. So, anyway, so yeah, at mode 7, there's actually just like no significant undershoot whatsoever at this point. And so we're actually just going to skip mode 8 LLC because mode 8 just has insane V-droop. In order to get like the load voltage to match up to like 1.24 volts mode 1. At mode 8, you need to be at like 1.545 volts, or I think maybe even 1.55, because apparently my pre-testing has like shifted for mode 7, so mode 8 might also be a bit low. Actually, yeah, mode 8 would be a bit low. So we would need to set mode 8 to like 1.55 volts in order to get the similar voltage to what we were getting with 1.24 mode 1. And yeah, I'm not going to do that. That's, like, there's just simply no reason to use mode 8 LLC due to just how insane the amount of V-droop on it is. So next what we're going to do is we're going to go back all the way to mode 1 again, and we're going to switch over to Socket Sense. And then we're going to set this to 1.24. And save and restart. And this video is getting way longer than I wanted it to be, but oh well. not my fault that MSI has more LLC settings than everybody else does, mostly because of the VCC socket sense thing and like socket sense thing. It's kind of funny. Like, there's some motherboards where it's like, oh, I really wish this had more LLC settings. And then there's MSI boards where it's like, actually, could we have less, please? Because I did test every single combination of, like, socket sense and VCC sense with every single mode of LLC. Because they don't even, like, they don't match up when you change the socket, like when you switch over from VCC sense to socket sense. So anyway, the thing that changes, like the main difference, like, so one, going from VCC sense to socket sense changes your load line slopes, which doesn't affect mode 1 because mode 1 has 0 V-droop. Therefore, it doesn't have a load line slope, right? The slope is flat. So it doesn't change. But the other thing it does, but all the other LLCs, like, they'll actually, like, going from VCC sense to socket sense, all your other LLCs will actually have more V-droop to them than they had before. So, anyway, yeah, so now what you're going to notice is that our Vcore reading over here is actually even further away from our VR out reading, and that's why, like, MSI calls it, like that's like the legacy way of doing Super I/O core voltage readings on motherboards. Like that's the norm. Is your motherboard measures the Super I/O chip of your motherboard measures the core voltage on the back, like somewhere, usually somewhere near the middle of the CPU socket on the back, like, you know, on the board. Not it doesn't get a core voltage reading from the DieSense circuitry that the VRM uses for core voltage regulation. So yeah, and now you can see that actually our Vcore reading, like, from the motherboard is straight up higher than what we're getting on the oscilloscope. And so this actually might be somewhere halfway up the power plane or something. And then our VR out sensor is still 1.24 volts. Right, so that's the main difference. Is like if you're on VCC sense, it's still not going to match the VR out sensor because I actually don't know how, like, what MSI did for the VCC sense thing. But when you're on socket sense, your Vcore VRM, like your Vcore reading from the Super I/O is like really, really high relative to the VR out reading. And this is normal. This is actually how it behaves on most motherboards, like on normal motherboards that don't have this like VCC sense, socket sense option in the BIOS. Anyway, even if you're on socket sense and you're on mode 1 LLC, the voltage regulation is still trash. So, yeah, no surprises there. We don't really need to worry about, like, not having, like, how you measure your core voltage doesn't matter if you don't have V-droop. It's still bad. So, so anyway, let's move on to LLC settings that you would actually realistically want to use, maybe. Like mode 4, which now sits at 1.365 volts, so it's a little bit more undershoot on... Like, mode 4 with socket sense has a bit more undershoot than mode 5 with VCC sense. And, like, optimal LLC, I'd say, is, like, mode 5 with socket sense. But anyway, we're going to take a look at mode 4, just to give you some idea of what it looks like. It's not too bad. So, yeah, now we're going to go to mode 4. And we are on socket sense, and now we're going to go all the way up to 1.365 volts. Also, we're no longer going to be consulting the VR out sensor. I mean, well, okay, we're not going to worry about it as much. Yeah, no, we're not going to bother with checking it again. Like, the thing is, as long as if the VR out sensor reads the same voltage, then we get the same voltage on the oscilloscope. And on the oscilloscope, we want to be seeing around 1.3 volts. Because if there's 1.3 volts on the oscilloscope, then there's probably around 60 millivolts less at the actual silicon, right? Because the resistance of the socket doesn't really change. I mean, it does, depending on how hot the socket is, and, you know, but, like... for like not enough to really like matter in this scenario. So I'm not gonna, like, I've done the pre-testing. I'm just not, I don't want to deal with opening hardware info all the time. So anyway, that's mode 4 with socket sense. We're gonna quickly clear the measurements, we're getting our average voltage of around 1.3 volts, which is our target. And then if I start moving the mouse around, it's performing better than it did in pre-testing, which is interesting. Wait, does opening hardware info might actually affect the measurements? Right, because we're basically relying on, like, Windows creating the transients, so depending on how much stuff is open, that would actually potentially affect it. Which is, yeah, so VR out is still 1.24. And now if I move the mouse now that hardware info is open, it looks like Windows has a bit more work to do with the input processing. So yeah, we're seeing like 1.264 volts from our average of 1.3, so that's what, like 35, 36 millivolts of undershoot. Not terrible. Yeah, like this really isn't that bad. And you wouldn't expect it to be that bad because it's a similar amount of V-droop to what we had when we were on mode 6 with VCC Sense. So, yeah. Anyway, we're gonna now switch over to mode 5. Is it mode 5? Yes, mode 5, which is basically mode 5 on socket sense, which is basically ideal. That's like the least amount of V-droop you need in order to get basically no significant undershoot on the back of the CPU socket. Also, mode 6 performs like, on socket sense, mode 6 behaves like mode 7 on VCC sense. So actually, I'm just not going to bother testing that. I'm gonna post the pre-testing notes in a comment or something. So anyway, now we're going to go up to 1.405. We're going to go to mode 5. Oh, actually, we will be going to mode 6, because that's what I used in pre-testing, that's what I used load line saturation with, so we need to go to mode 6. So, anyway, now what we're going to do is we're just going to run, I am going to open hardware info again. For that to open. Now if I open Y-Cruncher, again, our average voltage is at around, right, we need to reset the statistics. We're, again, at around 1.3 volts. If I don't move the mouse around, we're seeing like 18 millivolts, 20 millivolts of undershoot. If I do move the mouse around, we see 18, 20 millivolts of undershoot. It's great. That's what we want to see. Okay, like if I move it around long enough. That's actually one interesting thing I've noticed with this board. It seems that the voltage regulation of the VRM gets slightly worse as the VRM heats up. Well, slightly worse if you're on the sensible LLCs. If you're on mode 1, it actually goes from like looking okay at very low VRM temperatures to the like horrible, massive overshoot that we were seeing earlier in the video with mode 1. So yeah, mode 5 with socket sense is great. Like it just does an excellent job. There's very little undershoot. You don't need, like, your idle voltage isn't even that high. If we go down to the VR out sensor, you can see that we're at 1.237. So again, not perfectly matched, but actually it's 1.24 right now. But pretty close to spot on to that like 1.24 target that I have for this test scenario. And yeah, so that's like optimal settings for the Z790 Godlike. I'm not sure if these settings are applicable to any other MSI Z790 boards, because obviously this thing has a very, well, like the VRM on this is actually quite different from what you get on most of the other boards, especially in terms of the capacitor configuration, which in theory, would have the most impact on the undershoot, is what capacitor configuration the board comes with. But I've not tested any other... Well, I mean, I tested the ITX MSI board, but I don't remember anything from that testing, so that's not helpful. Anyway, so now let's take a look at the load line saturation setting. And this video is going to be an hour. Great. Anyway, so now we're going to go up to 1.455 volts, and we're going to switch to mode 6, and we're going to start with no load line saturation initially, so that you know, can see what actually, like, load line saturation does. Okay, so now we're in Windows, and nope. I mean, we do need hardware info again, because for the VR Vout readings, but I clicked on the wrong thing. So anyway, right now our idle voltage is like 1.424 volts. So I'm just going to put this down here-ish. Right, so we're at like 1.424 volts, and now if I run Y-Cruncher, we drop down to 1.24-ish. Right, which is the target. On the oscilloscope, we're getting, on the oscilloscope, we're getting our 1.3-ish volts. If I clear this, you can see that moving the mouse around doesn't really introduce any significant undershoot, but it's also not like this is comparable to what we were getting on mode 5 in terms of undershoot. So yeah, actually, like, it's very much comparable to what we were getting on mode 5. So anyway, so this is 1.455 volts with mode 6, and the cool thing with load line saturation is, like, well, what if I want the CPU to idle at like 1.4 volts instead of 1.45? Well, you can use load line saturation to do that, which basically the way that seems to work is that MSI just removes a portion of the, like, current for VDroop. So you basically, so the way we're going to set it up right now is I'm going to set a load line saturation of 75 amps, and basically the VRM is going to have no VDroop for the first 75 amps of load. And this is fine, because that's not enough current to cause, like, significant undershoot or anything, right? So we're going to enable it, set it to 75 amps. And I'm going to set the core voltage to 1.4. We're actually going to end up with the same load voltage, but significantly lower idle. And this is a feature that MSI has on every single one of their Z790 boards. And honestly, I think on most boards, you are probably, like, I think somewhere between 75 and maybe even like 125 amps of load line saturation, especially if you have the 13900K. Obviously, if you have a lower core count CPU, it might work out differently. But if you have a 13900K, then something between like 75 and 125 amps, and then just use the mode 6 socket sense LLC, I think that'll generally get you very good voltage regulation. Because MSI is actually relatively, like, yeah, they're relatively consistent in terms of how much VDroop their, like, various modes on their boards are. Unlike some manufacturers where each board has like completely different load line slopes for everything. Well, actually, it depends. It depends on the generation of motherboard, because certain generations of motherboards, some manufacturer, like like a lot of manufacturers will just use the same voltage like VRM controller for every single board. But if there's like a big variety of VRM controllers, you get a big variety of like load line slopes from board to board. So like medium LLC on one board won't be the same as medium LLC on another. Anyway, where's my VRV out sensor? There. So you can see we're back at 1.42 volts. And now if I stop the workload, we're at 1.4 idle instead of like, what was it? I think like 1.42 something previously. Anyway, if I run Y Cruncher again, right, and I move the mouse around, there's not really any significant undershoot, which is good. That's what we want. So that's actually really, really cool. And then I also get to keep the like low idle voltage. Now, what you will notice is that we actually have a slight overshoot. Very, very slight overshoot at idle. Because basically the way the load line saturation works is for low current, the VRM basically has no V-droop. Right? So until the CPU starts pulling more than 75 amps, there's no V-droop. So at low current loads, the voltage regulation actually suffers, but that doesn't really matter because at low load currents, you don't get big transients. Right? Because in order to get a really big, in order to get a large undershoot, you need a large amount of, a large increase in current demand. And in order to get a large overshoot, you need a big you need to go from pulling a lot of current to pulling very little current. So you need the CPU to go from, very, very low resistance to go to very high resistance. Whereas if the CPU is at, medium resistance, and then it goes to high resistance, well, that doesn't, yeah, it produces some overshoot, but it doesn't produce huge amounts of it. So it doesn't really matter that we don't have any load line to sort of absorb that overshoot. So yeah, it does make your peak to peak at actually it doesn't even affect the peak to peak, but it does you do get some extra overshoot at idle, but it doesn't directly translate into but your average voltage is lower, right? So your idle power consumption and your low load power consumption is actually going to be lower with this configuration than if you just have no load line saturation and you have tons of V-droop. That's one of the main downsides to just having really high V-droop LLCs is yeah, your 100% load voltage regulation is great, but now your idle voltage is sky high. So if your CPU is pulling between say 10 and so at idle, and the thing is, if the CPU is true idle, then the fact that the CPU is at 1.5 volts or 1 volts doesn't really matter because yeah, your power consumption actually increases quite a lot, but you're going from say 5 watts to 7 watts or 10 watts to 15, which is in terms of percentages, that's a big increase, right? If going from 10 to 15 watts idle, that's a 50% increase in idle power consumption, but it's 5 watts. It's it's just not that much power. But you do still have the issue of well, if you're at partial load, right, where where instead of pulling 10 watts, let's say you're pulling 50. Well, at 50 watts, now, now the fact that your idle voltage is really high is actually starts kind of significantly increasing your power consumption for medium load scenarios. So the load line saturation function that MSI has is really cool. Yeah, it is really cool, and it would be neat if it was present on more motherboards, but yeah, I've never MSI came up with it and I've not seen anybody else implement anything similar. Anyway, let's do something really dumb. We're going to set the load line saturation to 300 amps, which effectively turns mode 6 LLC into mode 1. Yeah, so though funnily enough, it doesn't suffer from the massive overshoot that mode 1 suffers from, which is really interesting. Yeah, that's going to be very, very interesting. So on mode 1, right, not only did we have, heaps of undershoot, we also had, those massive upward voltage spikes, which, again, not really, with the settings I was using here, they weren't high enough to really be dangerous, but, it's not great. And yeah, well, if you do this with the load line saturation, you don't get those massive upward spikes. Like, you do still get overshoot because there's no V-droop anymore. Like, you can already see just getting into Windows, our voltage regulation is spiking in both directions. Or more like our core voltage is spiking in both directions. Voltage regulation is like how voltage ends up doing that. And anyway, now if we hit Y Cruncher, and I am a little high on the voltage, but yeah. This is like, functionally, this is basically mode 1 LLC with extra steps. Though it doesn't do that like crazy overshoot. All right. So that is quite interesting that, like, for whatever reason, like, there's a lot of undershoot, but there's no massive upward spikes. And I'm actually going to quickly switch over to mode 1 without the load line saturation turned on, just to show the, like, big spikes. So yeah, if you're going to use the load line saturation, don't just set it to like 300 amps. That kind of defeats the purpose of using a high V-droop LLC. Okay, so we're going to go to 1.24. I'm going to switch this to mode 1, and we're going to go back to auto load line saturation. Actually, yeah, auto, and that should turn it off again. And this is just as like a quick reminder of like why mode 1 is so freaking bad. Because it is, and should not be used. Okay, and now we're just going to quickly hit Y Cruncher. I did it too quickly. There. So the funny thing is, like, initially, right, we don't really see... Oh, and yeah, and after, like, some warm-up period, the VRM starts producing these massive spikes on mode 1. So, yeah, mode 1 on this board has issues. Major issues. Because, like the undershoot is like, okay, that you see that on every board, but the 1.5, you know, like the overshoot being like 200 plus millivolts, I can't think of too many boards that do that, even if you max out the LLC. So yeah, really not sure what's going on with that. So yeah, like maxing out the load line saturation on something like mode 6 LLC is actually better than mode 1, but I wouldn't consider either of them ideal. So anyway, that's it. So that's the core voltage regulation on the Z790 Godlike. Mode 1 is bad, like very bad. I think this might actually be like one of the worst zero V-droop LLCs that I've seen on a Z790 motherboard. But yeah, then once you get to like I think optimal is like socket sense and then like mode 5 LLC. That's like optimal for this board. And then if you want to mess with the load line saturation, you can use even higher amounts of V-droop than mode 5 on socket sense. But mode 5 socket sense seems to be like, if you don't want to, you know, mess with the load line saturation feature, like mode 5 socket sense is kind of ideal in terms of voltage regulation. So yeah, and even mode 4 on socket sense is not too bad. And I wouldn't really recommend using the VCC sense, because you basically like you have very, like, your first, like, going from mode 1 to 5, you only get a voltage difference of like 55 millivolts, which is not really enough of a range of like settings to really tune your, like, it's not great, right? Like, you just don't have a lot of adjustment range on VCC Sense. Also, the board has VR Vout support in hardware info, so like, why would you use the VCC Sense functionality when hardware info can just read the core voltage directly from the VRM? Yeah. So that's kind of that. And I think that's actually like the VR Vout sensor is available for a lot of MSI boards. If I remember correctly, the ITX MSI board also has it accessible in hardware info. So same thing's true there in terms of like, I wouldn't really recommend using the VCC Sense mode on the MSI Z790 boards. So yeah, anyway, that's it for the video. Hopefully it was somewhat interesting, or maybe helpful, but yeah, that's it. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp, so if you'd like to check that out, there's a link to that down in the description below as well. And that's it for the video, so thank you for watching, and goodbye.